Okay, great. Yes, so thank you so much for joining the Big Data Derby 2022 first place winners call. Like I said, my name is Ashley. I'm the Kaggle competition program manager. I'll pass it maybe, let me see, maybe to Kimberly in my first screen. So I'll pass it to you for the first, quick intro, and then we can kickstart.
Okay, great. So I'm Kim. I'm currently a master's student at Simon Fraser University. Yeah, it's great to meet everyone and to be here to talk about our project. Do you want us to do the rounds of the whole group or just introduce ourselves in our presentation?
Yeah, maybe around the whole group very quickly.
Okay, yeah. Sure. Maybe Brendan can go next.
All right, yeah, for sure. So I'm Brendan. I'm also a current, I guess recent graduate from the Masters of Statistics program at Simon Fraser University, and I'm a data scientist at Zealous Analytics. And I'll pass it over to Tyrell next.
Hi, I'm Tyrell Stokes. I'm a postdoc at New York University and also a data scientist at Zealous Analytics.
And my name is Gurashish, and I'm also a master's student at SFU pursuing statistics. And nice to see you all.
Okay. I'll start from our side. I'm Joe Applebaum. I'm president of the New York Thoroughbred Horsemen's Association and one of the sponsors of the competition.
I'm Joe. Yep, Joe Longo, general manager here at the New York Racing Association, and in addition, one of the sponsors of the competition. So nice to meet you all.
And finally, Wande, don't forget about yourself.
Yeah, I'm Wande Owens. I'm currently a senior at Yale, and I'm interning with Mr. Applebaum this spring.
Great. Thank you so much for the quick intro. So maybe maybe Kimberly or anyone in the winner side can present the presentation, and then we can start walk through the whole solution. And we'll leave some time for the Q&A at the end. So yeah, take it all the way. Thank you. Sorry, Brendan, you're muted.
All good now?
Yes, looks good.
All right. So yeah, I guess I'll get started. So yeah, we're here today to talk about our presentation on Bayesian velocity models for horse race simulation for the 2022 Big Data Derby. And before we begin, we just want to give a big thank you to Kaggle, the NYTHA, the NYRA, and everyone involved in putting together this competition. As a group of young professionals and students that are doing research in sports analytics, it was super cool to get to work with this sort of new frontier of data in sports analytics with the horse racing tracking data. And yeah, it was really exciting to apply some of the stuff that we've done in other sports into the horse racing domain. And we'll kick things off with a bit of background about ourselves. So yeah, this is our team here. Like we mentioned off the top, we have 3 master's students at Simon Fraser University, Kimberly Kroetch, Gurashish Bagga, and myself, Brendan Kumagai, as well as Tyrell Stokes, who's a postdoc at NYU, and Liam Welsh, who's a PhD candidate at the University of Toronto. So for our submission, we focused on building a model that at any point of the race can forecast the probability that any horse will finish in any given finish placement, like first, second, third, and beyond. So with this model, we basically built out a Bayesian B-spline regression to predict the forward and lateral movement of every horse over the next frame, or 0.25 seconds. Then we built out a process to kind of simulate from this model over and over and over, and repeatedly move through the frames until every horse crossed the finish line. And from that simulation process, we're able to obtain estimates of sort of the probability that each horse will finish in any given placement. So the tools that we used to build out this model framework and simulation process were R and Stan, but we also use OpenFOAM and Blender as 2 other open source software for 3D modeling. which we'll talk about a little bit later, as that was a big part of our feature engineering in building out a 3D drafting model. So for these two movement models I mentioned, it takes approximately 10 hours to fit both of them. However, there is a bit of additional time for like data preparation, building out that 3D drafting model and simulating from this model. And I have some key features listed here, but I'm just going to skip over them for now because I'll touch back on them in about a minute or so. So just to lay out the game plan for this talk, we're going to kick things off by talking about data preparation and feature engineering. Then we're going to move on to using those features that we get from the first stage to build out our forward and lateral movement models. Once we have those models, we're going to simulate race outcomes or like simulate from those models to obtain like probabilities that any horse will finish in any given placement. And from there, we can use these simulations to obtain applications that we can apply directly to horse racing. So for the first step, we're going to talk about data prep and feature engineering. And with the data prep, with this competition, we were given tracking data for the horses in terms of longitude and latitude at every 0.25 seconds. So one of the things that we wanted to do here was add a bit of context to that. And the main thing that we did is to grab the track outline and finish line through manual data collection via Google Earth. So that's how we get this sort of visual that we have here. And there's a couple of other steps needed to sort of get this nice clean visual here. The first is that we interpolated along the track outlines at every 10 centimeters so that we're able to approximate where each horse lies on the track up to about 10 centimeters there. And then on top of that, we also divided the track into different stages like turns, stretches, and chutes using some geometry tricks. And there's several other steps here that we did to make the data more palatable for modeling, like imputing horse trajectories, converting coordinates from longitude and latitude to meters, and a few other things. But the main thing here is that we have the track and we're able to obtain where roughly the horse is in the race and how far the horse has traveled along the track. In terms of feature engineering, we divided our features into two different groups. The first is dynamic within race features. So these include things like distance measures, horse placements, information about drafting, and information about the track location. And basically, these are things that dynamically will update frame by frame during the race. So they're never going to stay static throughout the whole race. And on the right here, we have our second group of features, which are sort of random effects. So these are things like race context, horse, and jockeys that will all affect how fast a horse is going. So we'll kind of flip the order in here and how we go into kind of talking about these features in depth and talk about the random effects first now. So with the random effects on the top left, we have our jockey effect. And as you can see here, we have sort of a value for each jockey that's sort of the jockey's impact on the horse's speed. And same thing for the track effect on the bottom right. So depending on what type of track you're on and the condition, there's a single value that will kind of represent an impact on the horse's speed as well. On the right-hand side, we have our horse effect, which is a bit more in-depth or a bit trickier than just a single number value for each horse. So here we have a whole spline, which is sort of like a smooth curve, as you can see here, that will change as the race goes on from 0 meters traveled up until 1 mile. And you can see here that as the race goes on, say early on in the race, you'll notice that, say these are sort of 3 different groups of horses, but each horse will sort of have its individual curve. But you'll notice that some horses are a bit slower out of the starting gates. Some are a bit quicker at getting up to top speed or accelerating up to top speed. And some are good at having a nice sprint right at the finish or kind of conserving energy enough to have a nice finish. And moving back to that first group of covariates that I mentioned with the dynamic within race features, one thing we wanted to highlight was distance measures. So with distance measures, we sort of looked at 3 different types of distances: the forward distance and the Euclidean distance, which we calculate for each horse. We're looking at the nearest horse in front and behind and calculating the forward and Euclidean distance to that horse. And then also the lateral distance for the nearest horse to the right and to the left of each horse. And by obtaining these distances for each horse, we're kind of trying to characterize like the structure of, or like sort of the placement of the horse relative to the others, and kind of seeing how much room the horse has, and if it makes sense that he'll be able to kind of move to the right or to the left, or move forward to a certain degree, depending on like how crowded he is or how much space he has. And now I'll pass it over to Gurashish to talk a little bit about our drafting model.
All right, so I'd actually like to quickly go over this slide, and yeah, I'll explain all the steps that we took to create this drafting model. The first step was, of course, to create a 3D model of the horse and jockey, and for this we used an open source software called Blender, which is a 3D modeling software. And to create this model, we just sort of used a 2D image of the horse and tried to sort of extrapolate the 3D model. If we do a more realistic model of this, the results will probably change a bit more than what they are right now. And then I would say the step 2, 3, and 4 are probably the most important parts of the drafting model. Step 2 being adjusting the geometry of the horse, because once you have a 3D model, what you have to do is you need to take care of the topology of the horse, which means you have to make it smoother from the outside so that it'll be easier for us to conduct this step 4, which is discretizing the geometry, where we break the horse into very small parts. So after adjusting the geometry, the step 3 would be to create an inlet-outlet system, which really means is we need to take care of all the outdoor designs. For example, the fields are open, so we need to take care of our floors and walls and how big they should be in a way. And I chose to make our walls and floors and everything really huge compared to our horses, so that they don't really have an impact, since our fields are outdoors and we don't really want to have an impact from the walls and floors and anything else. Then what happens here is we used an open source software called OpenFoam that conducts all the fluid dynamic simulations that we need to get these charts and all the calculations that we need. The way it does that is by discretizing the geometry. What that really means is that it takes the horse and it takes the jockey and breaks it into very small parts. You can think of it sort of as an integral. You can break it into very small parts, and then you can calculate pressure on each of the tiny parts and then add up all of them. OpenFoam uses a specific algorithm to do that called PISO, which stands for the pressure impact by the splitting of operators. It's just a finite element method that they use to solve the Navier-Stokes equation. And once we calculate our pressures, we can get everything we want: force, energy, or power used by the horses. And through these, we can calculate all our metrics that we want, like the energy saved by the horse and all those kind of things. The important decisions that were involved was to choose the velocity that we want to use, because, of course, with different velocity, the drafting effect changes. And these are some of the visuals that I was able to get to make things a lot more clear. So the red area, of course, pretty much defines that the horse has to fight a lot of air resistance in the front, which makes sense. And the yellow part, of course, sort of says that it gets a bit lower. The air resistance here is a bit easier to fight with. And we can see that here. The second picture makes it a lot more clear. Like in front of the first horse, we see that everything is red here, which means there is a lot of air resistance that the horse is trying to fight. But here, for the second horse, it's pretty much yellow, which means the horse is probably saving some energy there. So we use these sort of techniques to come up with a feature for drafting and use it in our model. Now I'll pass this on to Tyrell to talk about the model that we used.
Sure, thanks. So yeah, now that we have sort of talked about, like, these are kind of the main features that we're trying to get, we want to kind of talk a little bit about the sort of main idea of the model and maybe situating it more broadly in the context of other sort of sports that have tracking data, which some of us have sort of experience with. So the really big idea is that we want to think about, we know that sort of at the frame level, that horses are sort of making two types of movements. they're moving like forward or perpendicular to the track. And ultimately at the end of the race, what matters is sort of like race distance. Like you need to, if you're doing a mile race, you need to do a mile with respect to sort of race distance. But we also know that there's a lot of strategy in terms of where you are in different lanes, and a lot of that strategy seems to be carried out by sort of how you position yourself, like left and right. So that's the real big idea. Is we thought a lot about how could you sort of make a model like this, and the easiest seemed to be to try to model them essentially separately. We allow sort of some dependence between them, but we have one model that sort of is predicting how far forward are you going to go in every frame, and we have another model that is predicting how far sideways. And given the kind of features that Gerashish and Brendan were talking about, we want to take into account that especially the lateral movement is going to depend on where the horse is with respect to all the other horses. So that's kind of like the really main key idea, and we think this is a good framework generally to build on. And I think that was like our main kind of goal with this, is we wanted to sort of set a mathematical framework that in the future, other people, in particular other people that know more about horse racing, could kind of use the structure that we developed to make even more realistic things. And just to kind of like situate that maybe more generally in other tracking data sort of sports, good examples would be, say, soccer, basketball, hockey. Once tracking data becomes available in these sports, there's often becomes a need for what we might call like a workhorse model. And something that all of those sports share in common, and horse racing as well, is there's something very complicated about like the natural measures of value happen at the end. Like say in soccer, its goal is the natural measure of value. In the case of horse racing, it's whether you win or what sort of place that you get. But a lot of the questions that we have really happen far away from that signal. And you can do a lot of simple analyses where, let's say, you can make like a simple indicator about whether somebody's drafting or not, and you can try to tie that to the end result. But we sort of know that these analyses are subject to all kinds of biases. And the solution that has been proposed in things like soccer and basketball and hockey is you want to make a dynamic model that is able to link the things that are happening on this very small scale to the end results at the end, like winning or what place that you get. And so that's a big part of why we want to build this at sort of a frame level. We want to separate out sort of forward and lateral movements. And we want to do so in a way that's going to be able to link what's going on at this micro level, these small decisions of like moving left or right, or like expending your energy or choosing to draft. And how can we like link that to the thing that's valuable, which is winning or your place that you get at the end. So that's really where we're kind of coming from. And we want to sort of have a framework that people can kind of like build on to make even better versions of that, and hopefully answer even more interesting questions that don't rely on these sort of static analyses. A really big component, if we go to the next slide, a really big component of that is essentially the simulation framework. And basically, once you have the models at the frame level, we need to be able to go through what we would think of as essentially like race paths. So the framework that we use in terms of actual modeling is a Bayesian framework. And one of the nice things about a Bayesian framework is there's a huge emphasis on what we call propagating uncertainty. And so we make our models, there's some uncertainty or some error involved in that. There's, in some sense, we're observing things that are probabilistic, but what we want to do is we want to like represent that forward. And simulation is a really good way to do that, where at each frame, we're able to take draws from like some distribution of where we expect this horse to go forward, where each horse expects to go left and right. And because all of our features in those models are dynamic, so now that you've taken one draw, you update the location of all of the different horses and where they are. And that's going to change like whether there's space on the inside or the outside of the horse, whether there's space forward or back. And each time you take a different draw like that, you're going to get slightly different dynamics. And so the simulation framework is a way of sort of like averaging over all of those and getting a sense of different possible race paths and finding out which ones are likely and which ones are less likely. This is also probably, from a coding standpoint, I think was the most difficult part of how can we make a framework that's going to allow us to simulate any race from essentially any starting position in a way that's efficient. We could talk a little bit more in details how we sort of went about solving that problem, but I think it's worth pointing out that that was probably the largest technical challenge.
Carol, can I ask a question there? I guess if you're doing that simulation, I guess you could conceivably do scenario. I'm just saying, like you could create scenarios, like if you wanted to train a jockey, like here you went outside, but let's look at what the scenario, how this would play out if you went inside, or if you decided to accelerate at a certain point, or whatever.
That's like what we kind of have in mind, like especially like I think we maybe weren't quite at that stage, but some of the things that we were thinking of is like you would have to build some more stuff on top of what we have to make it more like user friendly. But essentially you could take any combination of horses and you could drag and drop the horses in different positions, and then you could play out the race from that position. And that could maybe get at some of the questions that you're talking about, is like, oh, what if you would spend like a little bit extra energy early up and now you're closer to the pack, or if you had moved left or if you'd moved right. That's kind of what we would hope this kind of model could get to. And I think a lot of the structure for being able to do that kind of analysis is here. We would need, I think, more input from like people that understand horse racing better, but like I think mathematically we were trying to make something that is like capable of that sort of analysis.
Okay, great.
Okay, so I will go over some of the key findings from our model application. So starting with the dynamic finishing position probabilities. So here we have on the right the progression of one of the Belmont Park races. And on the left, you can see a heat map, which gives our models predicted finishing place probabilities for each of the horse jockey pairs. And you can see that it's being updated as the race progresses and the model can take in new information until it finally converges onto the actual result of the race. And just note here the horse in yellow, which is Curlin's New Moon. You can see at the beginning that he's legging back a little bit, about 5th or 6th place. But despite this, our model is predicting a high finishing place for him right from the start of the race. And this is sort of demonstrating how our model can take in key features like the fact that at the beginning, you can see he's in a drafting position behind another horse. So our model can take in information such as that and all of the other features we've included and predict a high finishing place for him, even though he's lagging back at the start. And then you can see in the end, he does pull forward. And in this particular race, he finishes in 2nd place.
Hey, Kim, can I just ask a question? Every horse at the beginning of the race starts with an equal probability, or is there some probability? I know that's a big issue in other sports and win probability. You know, is it just that game? Are we giving them a pre-rating? Like, how do you guys do that?
Well, it's basically based on all of the other like races that we've included and the other contextual features in the race itself. So they're not starting with an equal probability. It's based on like the locations that they are starting in and how they've been moving previously throughout the race, but also things like the jockey and just the horse, how the horse has performed previously and things like that.
Okay, so there is some level of rating of the horse / jockey in that.
Yes.
Okay.
Yeah.
No, good to know. I just wanted to clarify.
Yeah, no, for sure. Okay, so getting into our next result here. So Brendan touched on this a bit earlier, so I won't spend too much time on it, but one of the big parts of this project was the inclusion of the spline effect for each horse. So what this does is we're basically getting what we're calling a horse profile, which sort of summarizes the horse's speed tendencies throughout a race. And what we've done is with our model results, we've obtained a horse profile for each horse. and we decided to cluster them. So we've obtained 3 different groups here, and each horse can be sort of roughly described as falling into one of these categories in general. So on the left, we have this group described by this blue curve. And so these are horses who tend to accelerate hard over the first 100 or so meters of the race and then sort of trail off. And then in green, we have horses who take a bit longer to reach their top speed, but then they sort of maintain a high speed impact throughout the race. And at the end, you can see there's another little burst of energy at that final stretch. And then in red, there's this kind of in between where they're still taking a bit more time to reach top speed compared to the blue group, but then they kind of maintain their speed well throughout the rest of the race. And then lastly, I'll get into the jockey ratings. So from our model, we're also able to obtain these jockey ratings, which indicates like a higher rating will indicate that it's a higher skill for the jockey, and they have a more positive impact on the finishing place. So here we're giving our model's top 10 rated jockeys in order. And on the right, we have rankings obtained online for Saratoga, Belmont, and Aqueduct separately. And we're just comparing these to our model's ranking of the jockeys. And you can see that for the most part, all of our model's top jockeys are ranked really well in at least one of the 3 tracks. Specifically, the top jockey here is being ranked first in both Saratoga and Belmont, and then 4th in Aqueduct.
And that rating comes from what? From the decision, the paths they took, or like the efficiency of the path? What are you rating there? I guess is my.
So we include like a jockey effect into the model. So as the model's being trained, it's sort of deciding like which jockeys are in general producing or like resulting in a better finishing place.
So it's a result. Okay.
And just the next slide, Brendan. Okay, yeah, so in general, we've been talking about our full model that we implemented, but if you are interested in just a subset of the features we've included, we would recommend for the forward model using only the horse spline, jockey, and track effects. And then for the lateral movement, using only lateral location of the horse in the previous frame, and then the change in the lateral location over the previous 2 frames, so just how they were moving sideways beforehand, and distance metrics for the closest horse to the right and left. Just next slide, Brendan. Can you move to the next slide?
Nope.
Oh, is it not working?
I see value added from our work.
Oh, I do not. 1 second. Okay.
We're still on simple model, but that's okay.
Oh, sorry. Maybe I might have to just.
There you go.
There it is. Okay. 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 So what we've done is we've created a novel modeling framework for forecasting the outcome of a horse race and valuing a horse's position at any moment during a race. So we really want to look at like where's the horse in this given moment and how does that affect the long-term kind of value of how the race will play out. And 2 of the key aspects here were first that we incorporated that spline effect for each horse, which gives us a sense of how a horse's speed tendencies change as the race goes on. And the 3D drafting simulation model that Kroetch went over, which gives us more accurate estimates of the effect of drafting than previous approaches in the literature. Okay, but as always, there's improvements that could be made given more time, and I think especially in this case, given more consultation with horse racing experts. So we were really focused on getting this simulation framework up and running, but it would be nice to spend more time on model evaluation and feature selection. And it would also be nice to continue developing our Shiny app to provide users with an interactive tool where they can choose the track they want, choose the race conditions, choose their horses and jockeys and their starting posts, and then given those user-specified conditions, forecast the race outcomes. We would also like to expand the framework to all race lengths, as we were only looking at the 1 mile races. And then there are so many different applications that we could explore with this model framework. We only had time to explore a couple that we were hoping would be useful, but other areas that you could explore would be determining the effect of starting lane on win probability, analyzing optimal draft patterns, and estimating injury probability. And I think that is all that we have for now. So we'd love to hear your comments and questions. And yeah, thank you for listening.
That's great. First off, congratulations on winning, guys. It's an amazing effort. You clearly put in a lot of work. You thought it through, and you presented it well, which actually always amazes me. This is a little bit of an aside. Like I found, because it was an analytic contest and not a predictive contest, a lot of guys just throw their code up and then get angry with me, quite honestly, when I don't read their code line for line and tell them how good it is. It may be amazing. I don't know how to read code. Otherwise, I wouldn't be doing this. So I appreciate it, and I think that paid off. And if you saw most of the top efforts, they all had essentially a story to tell, right? We have, here's what we did, here was our theory, here's what we came up with. And it was all the top ones, I think, did a good job of storytelling, which was important. The other thing that I think worked especially in your favor, because it made a lot of the analysis very understandable, and Davis and Wande may not realize this, but you only used 1 mile races from Aqueduct, right? That was our most popular, right? Am I correct about that? Or 1 mile dirt races?
We used all 1 mile races.
All the 1 mile races.
Just
right?
visualize more from Belmont.
So it's very clear, right? And some guys are trying to look at multiple surfaces and multiple distances. It can make it a little less clear as to what the outcomes are. So I thought that was all good. I don't want to dominate the question, but let me ask one question, then I'll throw it to Joe or Davis or Wanda. So it took 10 hours to train the model, but if we were supplying data in real time, could the model predict? Could the model produce its winning? Let's call them win percentages or finish position percentages in a contemporaneous fashion. Is that not the right way to say it?
Yeah, no, I think I understand. For that, like, if you're talking about like during a race, like essentially all you'd have to be doing is running like the simulation part. Like you wouldn't have to retrain
Correct.
the model. Like, so we've separated those two things. Brendan can probably speak more to the exact time on that. I can't remember the exact numbers, but I think like you can do about 2,000 and about simulations in about a minute or something like that. Is that right, Brendan?
Yeah. So like if you take any given situation, it would take, it depends on how much time is left in the race. Like if you're closer to the finish, then it's going to be quicker since there's less distance to go. But yeah, it could take anywhere between like 30 seconds and about 75 seconds. That's what it seemed to run about on average for most races. So yeah, I think some work would have to be done there to really get it to be like real time. Like as the broadcast is going, you have that heat map going, but you could probably set it up to like retroactively, if you want to look back at a point on the broadcast, maybe when they're recapping the race, you could possibly have like a moment where you have that heat map up. But yeah, I think there's still a bit of work that would have to be done in probably converting some more of the R code into C++, which is a lot more efficient. I think that's part of the bottleneck, is running it for the whole race takes a while because you have to do frame by frame by frame for the entire race, which could take like an hour or so. But yeah, if you were to set that pipeline up in C++, I think that would reduce the time needed there by quite a bit. We do have the simulation set up in Sten, which is kind of run in C++, so that's going at like a pretty quick pace for kind of what we have to do. But yeah, I think there's still work that can be done there to make it more efficient and more something like that's more for a real-time broadcast.
Okay, that's interesting. Joe, what do you got?
It kind of took my thunder because I was thinking the same exact thing as it relates to like, you know, the Fox broadcast. If you think about like what we do with television, if you have that up there, and you know, we don't really do any in-race wagering here, but like when you to actually see that, that would actually be cool. But I think it's one of those things like anything else, you know, probably would get better with time or more efficient. But that's exactly the path I was going. When I first saw the original 10-hour, I'm like, all right, how can we get that down to like real time? But no, that was the one major thing I had. And I think even too, from when you said focusing on the mile distance, was this the mile across both surfaces? Yeah, because I was going to say at Saratoga, this data was from what, 19, Joe?
19, yeah.
Yeah, we didn't have a mile on the dirt back then. So that was all turf racing at Saratoga there.
Yeah. So we just took in like whichever 1 mile races.
Yep.
We kind of like when we were setting up our app, we weren't able to get it into production or like up online in time for the competition deadline. But we were having an internal debate like whether or not we should include tracks that weren't used, like say Saratoga, there's no 1 mile races. Should we include like hypothetically if you were to run on that, if that should be included? But yeah, that's something that we didn't really get to at that point, but we're just including everything we did have into the model for the 1 mile.
In terms of settling on the 1 mile distance, was that just the biggest sample size across all 3 tracks?
Yeah, I think so. Yeah, we just wanted to kind of fix more for like modeling purposes. We wanted to just fix on 1 distance, and 1 mile had quite a bit of data. I think like 1/5 of the data overall, maybe more. I can't remember exactly, but yeah, that just seemed like kind of a pretty clear, common one that we can use just to kind of get a first version of the model going.
Yep, I could just jump on that. Part of that was also with the horse spline effect. We're trying to show how the speed tendencies change over time, and as you differ the length of the races, that will start to make less and less sense aggregated over everything. Even within the 1 mile races, it doesn't perfectly work because you have still different like track shapes and sizes, but it at least makes a bit more sense than if we were to include all these different lengths of races.
Yeah, it's also interesting, I think, what the findings would be if you applied this model to a number of different tracks across the country, because, you know, Belmont, right, it's a 1-turn mile. So effectively it's an elongated sprint versus others that have a 2-turn mile where you're going to have a little, you know, change in their, you know, acceleration. So
Yeah, exactly.
But I thought it was pretty well done. Davis, do you have anything?
Yeah, that was great, guys. Definitely appreciate it, and congratulations once again. My thought, which I think would be really interesting to see, is we take these 1 mile races, but then being able to break it down by the condition of each race, like so horse level, to see if strategy or winning probability changes on the quality of horse based off where they are, from like a $10,000 claiming horse to a high level allowance horse, to see if that would differ in any way, if that would change the jockey strategy or the trainer strategy. That's just my 2 thoughts, and congrats again.
Yeah, that makes a lot of sense. I think we thought a little bit. I think maybe Kim touched on this at some point, but one of the kind of really difficult parts of a model like this is to try to like pull apart all of these effects that are like happening at the same time.
Right.
The sort of Bayesian framework, it can be a good one for that. And one of the things we definitely thought about was if we could kind of use those kinds of like dollar amounts that you're talking about, or even like the dollar amounts and like what the prize is, to help give us sort of like priors to help pull those things a priori. But we hadn't really thought about it on the other end of like using it as like a like a starting point for analysis. But I guess that's again the kind of stuff that we would know less about. That makes more sense.
You know, it's very interesting. And some other work that we've done, the characteristics of a horse stride, like around the turn, changes based off the quality of the horse. So it'd be interesting if that could line up with your all's model here. But yeah.
Yeah, can I pick up that thread for a second? So at the end of the day, we're very interested in like horse welfare and safety and longevity. So I guess it's a question to you guys, is using a model of, let's call it lateral and longitudinal velocity, could we model that for horses that, I mean, I guess you could, I guess, what is the likelihood of creating successful models using those inputs that might in the future predict horse longevity, or horses that might stop running, or like one of the things in a different presentation, these guys are probably sick of hearing me talk about that, is velocity, is the consistency of velocity, especially around the turn, seems like it's highly predictive of both current success and future success, right? It's less, horses don't seem, other than maybe the very finest, have the ability to go fast then slow, then fast then slow. Typically, the route to success for most is to have a consistent velocity, right? And not accelerate or decel too often. It's too hard. And so I guess picking up on Davis's thread, is there the ability potentially to look at both lateral, because that might be a huge lateral component, the more I think about it, like to look at lateral and longitudinal movements to say, so instead of isolating the horse, say this is the pattern that often horses that don't race frequently in the future develop.
Yeah.
Something like that. I don't know. I may be a little all over the place.
Joe, to piggyback on what you're saying, when I know I look at this a lot in harness racing in terms of how many moves does a horse have, right? So how much can you stop and start and stop and start? But this would be really interesting too, even on the harness racing side of things, just with how much of position and drafting actually comes into play, and how can you make the lead, take back, make the lead again. So, and I would imagine with Davis speaking across the different conditions, yeah, on the lower end of things, they probably have one move versus the higher up in class you get, the more they can do.
Yeah. So I don't know. It's kind of throwing it to you guys for like, is that something you think might be modelable? I don't know if that's a real word.
Yeah, I can talk a little bit about that. Like in my other life, I actually do a decent amount of injury modeling for like mostly like hockey and a few other sports.
Do you work for Zealous too? Does anyone not work for Zealous anymore?
I do work for Zealous, but I don't do injury stuff for that. I work with one of my PhD supervisors is a sports medicine physician, so I help him out with all kinds of different analysis that way. The one piece that I think like a model like this could help with, and maybe indirectly, a lot of what people do in this kind of like injury modeling world is essentially you're trying to make like sophisticated measures of like workload. And the kind of like cutting edge of that is in sort of like the bio mechanics type world, where often you have like a player that's like hooked up to some sort of a tracking type thing, and you're trying to figure out things like total distance, like speed, and like the kind of overall energy, and then also kind of like you guys are saying, like big sort of changes in energy, whether like left and right. And this model in itself is not like perfectly suited, I think, for that, but some of the same kinds of thinking could help for thinking about total energy expenditure, looking for big spikes. Like in other sort of sports, we look at like say in like soccer, you're really interested in large like velocity changes because we expect that those are going to have like larger impacts on like your knees and stuff. And I think that's a little bit similar to like these looking at these particular like turn type stuff. Injuries are hard though. Like it's a harder problem than most people I think want to admit, because I mean, I don't know horse racing well enough, but they're often rare. And then there's also like, there's the workload that happens during the race, but there's also the workload like off. So like the best teams that are doing this kind of stuff are not just having sort of workload information based on the games, but like it's a continuous monitoring of like all the practices and all these other, they're the athletes are waking up in the morning and are doing subjective like surveys about how they're feeling. That's all getting correlated to workload yesterday and in the previous days. I think the answer is like yes, but I think that's also like it's a hard problem. But the kind of thinking of trying to use tracking data to isolate, like you want to work with people that understand the physiology of like horses, but you can in principle use tracking data to sort of get at the like high impact and important things like that.
Yeah, well, that's actually exactly what we're doing or starting to do, and collect more data. We're hoping to get devices on our horses that can pick up heart rate, that are have more, I guess it's called gyroscopic information, right? That can analyze the actual movement of different limbs, as opposed to just kind of XY coordinate data. There's huge good news with horses as opposed to human athletes. There's not really a players association that you have to negotiate with. But the bad news is they can't put the devices on themselves. You know, you have to basically, you're doing everything for them. The other good news is that their movements are somewhat limited, right? They're either in the stall or they're on the track. Like they're not really like walking around in public or going to play basketball when they're not really supposed to, or whatever, you know. So those are some benefits to us. And this is where we're going, just what you were talking about. So to give you an idea, we'll have maybe for every 1,000 starters, we'll have about 1.2 catastrophic breakdowns in our circuit, right? And that's obviously a huge focus of what we want to prevent. The problem is, I don't know if this is exactly the law of small numbers, but you got the idea. It's such a small, tiny bullseye to hit. It's almost impossible, right? And it's actually a big fight we got into with a commercial group that was trying to predict those injuries. He's like, well, I wrote this model for your 15 breakdowns last year. And then he back tested it on those same horses. And of course he got like 95%. And I'm like, yeah, well, you wrote the model based on, it's almost too difficult to predict. So we were trying to expand our field to maybe have a better idea of predicting like subclinical injury, right? That'll give us a bigger bullseye that might be easier to, you know, and then you're hoping that you're reducing your catastrophics as kind of a second level effect of reducing injuries or catching injuries earlier. I guess it's not unlike they want to do with cancer, if you can catch cancer earlier. Although I don't know that that's actually the case in many cancers, but that's a whole other area. So anyway, that's I know I'm kind of free associating a little, but that's kind of the area we're headed in, and looking at presentations like this actually gives me a little bit of hope we might be successful, because of our, you know, some of the predictive ability.
Yeah, that makes a lot of sense. Yeah, I think like this, it for sure, you're like all the things you said sounds like you're in a great position to have really high quality predictors. Like, yeah, like you said, the outcome problem is a hard problem. That approach makes a lot of sense to me, of like, if you can talk to people that understand the sort of mechanism of the injuries, and you can especially link these like smaller sub ones to the bigger ones, that's you're on the track to do as good as you can do. Whether that's amazing or not is kind of sometimes just up to the.
We're working with veterinarians and other animal, I guess physiologists. I guess, is that the right name? Physiologists. You know, like to give you an example, in horses, you also, I think they call it cross-lateral injuries, right? So if the horse is hurt in his right front, it might not show up. It's often the left hind limb that actually shows, because that's where the compensation takes place. So it's all very kind of interesting and emerging, as they say, right? We're learning so much from so many different sources. Let me ask you guys, unless Wande, anyone else? Joe, any other questions before I launch into my other question? What do you think of the competition? I know some of you guys work, Brendan's like the Babe Ruth of competitions with his different victories. But like, I know you guys work with data from a bunch of other sports, many of you. What did we do well? How can we improve? What sort of other data is out there that we can be collecting and distributing that might be helpful? Or like one area of data that I know we have that we haven't linked to this is we have ground data, moisture data for our tracks. We have weather data. We actually have weather terminals on track that we think we can incorporate, which we think will be helpful. What I know you guys have vast experience throughout sports analytics, so I want to kind of pull on that a little. If you and be critical. We're not, we're not shrinking violets, I guess they're called.
Brendan, do you want to start with that, or?
Yeah, sure. Yeah. Yeah, that's a good question. Like, I know, like, say going through the data, we noticed like some, like, kind of sometimes the tracker might not be completely accurate all the time. I felt like that sometimes was a bit tricky to work with and identify like the issues at times. But at the same time, like say the Big Data Cup, which is sort of like a hockey type of equivalent by staffleets for this type of competition. So the first year they did it, they just released like event data. So you have passes, shots, this and that, like different kind of discrete events that are occurring at like different kind of time points. But they didn't have any tracking data with it. The next year when they came back, they had that same event data, but also added in tracking data, but they did like computer vision. So it was very, very difficult to work with. And it wasn't like unless you're like a data engineer and you spent hours and hours working through it, it would be kind of difficult to really make something useful of it. So really the number of participants in the first year versus the second year was a big drop just because the quality of the data went down. I think in this one here with the tracking data, there are like I think that like you guys still got a lot. You got like 106 or something in total.
Yeah, we were thrilled. Hey,
Yeah.
Joe Longo and I were like worried we weren't going to get like 20, right, Joe? Remember those conversations? Like we were like, oh, I hope 20 people submit, So yeah, we got 106, and like honestly, I felt there were like 15 to 20 pretty good ones, and then the four final. There were a couple like good ones that I think some people had some language issues were a problem because they would do good work, but the presentation wasn't as strong. But I was overwhelmed at like the quality of the presentations, and interestingly, some of the similar threads, even in presentations that looked strong on the math, but maybe not so strong on the presentation itself, found very similar results in various areas.
Okay. Yeah. Nice. Yeah. So yeah, that's like awesome. I think like to even get to the big data bowl type of level where they have like 300-400 submissions. I think part of what they like makes them so popular too is that their data, like it's pretty much flawless, and it's just like you take the data and you could go, you don't have to do any processing really, unless it's just for a particular type of model that you're building out. So yeah, like if you had some sort of data pipeline set up to take in what you kind of like the raw data you get with the longitude and latitude and that, and kind of set it up where it's just in a place where everything's smooth it out. There's not really any errors in it, or you kind of mitigate the errors to like as much as you can. I think that's what kind of like deterred people from joining the second Big Data Cup was just they had a lot of errors to work with. Like the data that you have now is already much, much cleaner than that for tracking data. So like I think though if it was set up where you kind of had some sort of like you had the track outlines, like we kind of gathered that manually, if that was sort of set up like and you had some sort of pipeline to have everything ready to go, I think that might help like expand the competition a bit more and get people interested that just want to like grab the data and run rather than doing a bit of preparation on top of that. That's just kind of,
Well, that's the number one criticism we've heard, is if we could have set up the track, I guess, parameters of the tracks themselves, that would have saved people a lot of work and time, I guess, right? It made it cleaner. Let me ask you, if we could expand, well, to like multiple tracks or multiple years, is that helpful, or how helpful might that be, or not so much?
If the way I would think about that is like, I think it would be like sort of depending on what you're hoping to get out of it. So like a project like ours, there's a lot of things that could have been helped by having more data. Like I think some of the estimates of like the effects that we have would be better, but we likely would have spent more time on the kind of computational side rather than the idea side. I think another thing that the football big data bowl does really well is every sort of year they kind of actually limit, like they're like, in this year, Brendan and other people would know better, but like it's like we're focusing on like punts, or we're focusing on special teams,
Right.
or like I sometimes there's natural constraints and limits. If what you're looking for out of it is like ideas for analysis, I think it's okay to have like the constraints, and it's not necessarily like the best to just give like as much as possible, because it can be a little bit overwhelming, and you might get a lot of people that just spend a lot of time just running really long models. But if that's part of what you're trying to get, if you're more interested in like actual results, maybe there's a bit of a trade-off there, but I think it would just be kind of like what you're hoping to produce out of the submissions.
Yeah, that's good feedback. I think one of the things for us is that we're in such, our analytics and horse racing is in such an infancy, like we almost don't know anything. So just getting basic like feedback on something like drafting, right, is like everyone assumed or didn't assume. No one knows anything. We're like very far behind. So I thought this first one, it was important to be a little bit open-ended to see, but you're right. Like a lot of people got caught up on like trying to predict winners, and like that's the last thing we need help with. Like we got 100 years of books on trying to predict winners, and like and using the movement stuff like to talk about drafting and jockey decisions. I thought was a much better, way to go.
I had a quick question, if that's okay. I was just wondering, like in the data, you guys have longitude and latitude position while tracking. Like, is there a particular reason you guys didn't go with like straight up XY coordinates like in the Euclidean plane and chose to go with longitude and latitude rather?
I'll be honest, we literally just gave you what we got from the company.
No.
Like it's literally like I took it. We have one guy who was able to link, right? So we get from the company a timestamp, an XY, and a horse ID, I think, or a post position number. I forget just one number. And the big thing that our database guy was able to do that literally no one else could do was link it to the relevant, like what I'll call handicapping data, the horse's name, the jockey's name, how much was bet on the horse, etc. And no one else, even in our sport, even knows how to do that right now. So literally, that's just like the data we get. So interestingly, that company has just gone out of business, and there are all sorts of other companies in this space. That company uses LPS, a local positioning system. So they actually put, I think, Davis, what's it like, 16 local monitors on the track, something like that?
Yeah, I believe they have one on each 16th pole. I could believe that's it.
About 16 reception devices. And so the units ping to that device, not to GPS, not to a satellite. Most of the new companies or the more modern companies are using some form of GPS, which, to be honest, when I'm watching the visual on the screen, is not as accurate. Although there's now a new form of GPS that is more accurate. And there's another one, they all something UFC, something field, I don't know. There's another one that they use that's also more accurate that I know Man City uses on their. One of the interesting things in talking with those guys was that they have 13 full pitch soccer, right? Most sports, even the NFL, you could fit 10 NFL fields into one of our racetracks. So that's difficult, right? But literally Man City, their training complex is like 13 fields. So it's actually pretty well sized. So solving some of those technical challenges is real in terms of getting, so we do a lot actually with the companies on mapping our properties to make sure that they're fairly accurate. But it's a great question, and it's something that Davis and I in particular are trying to learn on the fly because of this. And just to give you a little background, these companies all started the opposite of human sport companies, right? So Catapult is there for athletic performance or injury prevention. These companies and this data we're getting were all there to provide broadcast information. So we have little, even though AWS thinks they're inventing this now, Joe, for what, 10 years we've been doing it with the chiclets on the screen, right? Because most people don't know what they're seeing in a horse race. The horses obscure each other. So for years we've had these little dots essentially on the screen in different colors, so you know what your horse color number was. Anyway, that's a long answer to a direct question. But the real answer is I have no idea. They just gave us that stuff.
This would be something I would have less of an idea on how you would do it, but I could imagine it's a little bit tough. Good data engineers right now in all of tech are hard to get, and sports it's also true. But some of the stuff that you described, you could imagine maybe a smaller competition that is meant to solve the data problems, and at the very least it could be a pipeline for you guys to get data engineer talent essentially to help with those kinds of problems. Yeah, I don't know if that's something you're interested in, but I don't know if anybody's done that, but I think it could be interesting.
We are very interested in the pipeline because, like you say, it's hard to find people or find people interested or who are competent in working with this stuff. I think that's a huge advantage the NFL has, right? Is everyone wants to work for the Baltimore Ravens. So, and what's a better way to showcase your talents, right? Than come up with completion percentage over expectation, so that yes, that's also a thing, and it's going to be something our sport has to grapple with over the next coming years, as we've been doing it a lot with freelancers and a lot with students and such. Are we willing to invest in that sort of personnel, which are competitive, although less competitive these days with all the Silicon Valley layoffs? But yes, are we willing to invest in those sort of people to drive things forward? So, anyone else? Any questions, comments? Okay. Guys, it's been all. Guys, what's our situation? Is there a bit bucket with your code? Do we get that or we not get that? I don't know what we're supposed to be doing.
Yeah.
Ashley, is that a question for you or Addison or?
Yeah, that's a question to Addison or us, but so you should have, depending on your competition, you should be able to access your, like there should be a download page, like
Okay.
you can download the solutions, etc. So yeah,
Okay.
maybe I can look into that for you, like depending on your competition. You should have access to the competition, the host as
Oh,
the host,
yeah.
right? Like the pages, etc. So there should be a page that you can download the solution.
Okay. I will try to figure out how to do that.
Yeah, like I believe Addison should have sent you the instruction as well. Usually it's in our
Okay.
post competition instruction. But
Okay.
can we post it, or maybe Maggie too, because you're meeting Maggie in the later session as well, right?
Okay. Yes, I believe so. We met her earlier and
Yeah, one more session later.
yes. Okay. Guys, this is awesome. Thank you. This is great. Yes, if you could send the GitHub again, that would be make it easy. Awesome. Guys, thank you. Congratulations. Big win. And anyway, it's great to see you guys.
Yeah, nice seeing y'all.
Yeah.
Take care, guys.
Yeah,
Thanks
thank
again.
you guys.
Thank you. Bye-bye.
Thanks, yeah.